You are muted, David.
Thank you very much. Technical problems. So, excuse me. Sorry for this beginning. Welcome. Good afternoon, and welcome everyone to this series of webinars. Today we are doing the third series of webinars focused on the design and the development of digital tools for electrical vehicles. Today we have three presentations. We have three people that will present, which are Jose Saez from Envision and also from the RHODaS project, Albert Filba from the Iraq. He will talk for the SCAPE project, and finally Konstantinos Kostopoulos also from the UPC for the Maxima project. So we can start. So Jose.
Okay. Let me share quickly my screen. Thank you very much, David, for your introduction. Good afternoon, everybody. So yeah, first of all, we would like to start with our presentation about RHODaS project. The idea is to present to all of you the different digital tools that we have been developing during the project in order to manage the different potential faults and failures that might happen in electric vehicles. As you will see, of course, in this case, they will be very focused on the subsystem of an electric vehicle that has been addressed in RHODaS, but I think they are scale up. They could be scaled up to the other different systems or subsystems that are included in these vehicles. So first of all, to start, for all of you who are not familiar with RHODaS project, I would like to do a very short introduction about this project. The main objective of RHODaS project is to do some research and development in order to develop a new integrated motor drive for heavy-duty vehicles. So the idea is to provide some technological advance that leverage from the main advantages that can provide the wide bandgap semiconductors like silicon carbide and gallium nitride, and also some innovative multi-level inverter topologies like T-type in order to improve the integrated motor drive efficiency and also to increase the operating voltage and the switching frequency. These new inverter topologies and wide bandgap semiconductors are complemented with new or innovative advanced thermal management strategies, specially designed for this type of devices, as well as for the different digital tools, including a sensor network, a digital twin, and different AI-based functionalities that I will show later. So finally, the idea is to obtain, as you can see here in that image, a more integrated motor drive, which is able to reduce cost, size, and weight of the motor drive while increasing the lifetime, the efficiency, and especially the extended range. So in a very short way, this is a quick overview of the consortium that has been participating in RHODaS project and the different roles. Not to go too much into detail, but here you can see that the main partners, UPC has been the coordinator and working on the inverter, the power converter. NEIA is in charge of dissemination and communication activities. The Technical University of Vienna has been dealing with all the environmental assessment and circularity and criticality issues. The RHODaS University have been contributing in the thermal management system and also in the development of the digital twin. The Austrian Institute of Technology has been focused or is collaborating with UPC in the development of the power converter, especially on prototyping activities. Bosmal, an automotive company or testing company located in Poland, is in charge for all the validation and test for especially for the motor, the power converter and the gearbox, the whole integrated motor drive. Valeo and Valeo E-Automotive have been contributing in the development of the gearbox and the electric motor, respectively. And finally, emission, the company I'm representing, we have been in charge of the digital architecture and the digital platform that will be able to monitor the different subsystems developed in RHODaS, and also to manage the different or to provide the infrastructure for the fault management. So said that, and going into the details of this digital architecture, the first point would be to define or to explain a little bit which are the main objectives and functionalities that are expected from these digital tools. So within the project, as I mentioned before, the main focus or the core of the project is more related to the power electronics and the integration with the e-motor and the gearbox. But during project preparation, we want to take advantage from the new digital technologies, from the wave of AI and the other existing technologies like IoT and modeling architectures and modeling technologies, in order to improve the features and the performance of the integrated motor drive. So the idea is to be able to gather data from the whole system using a sensor network, okay, with a group of sensors that are placed in strategic points of the system, to define and to develop an IoT platform able to collect the data and to manage the data provided by all these sensors, and then to provide some more advanced features that using the data gathered by this IoT platform are able to provide more information, and especially to provide some analytics and insights about the operation of the integrated motor drive. These main tools have been a digital twin that will, as I will show later, will be very focused on the thermal behavior of the different components, some predictive maintenance functionalities based on artificial intelligence, but also some more simple rules. And finally, a decision support system, which is, let's say, the main point for managing or dealing with the different faults that has been detected. The final aim of all these technologies is to contribute to the KPIs defined in the project, specifically to those that you can see here on the right, which is reducing by 30% the failures of the system, reducing by 20% the cost. In this case, especially, we are focusing on the operating cost, not in the purchasing cost. And finally, also to increase lifetime thanks to this reduction in failures. So I would like to start giving you an overview of the whole digital architecture that we have been developing in the project. In a very simple way, this digital architecture has been divided into three main layers. The first layer is implemented on the local CPU in the control unit. This layer is, or this system is dealing mainly with those critical faults that require immediate actions to prevent damage on the integrated motor drive, especially on the motor and the power converter. So these are some algorithms, maybe more basic algorithms that in the other ones, which has been implemented in the microcontrollers driving the power converter and the motor, in order to prevent the most critical electrical and thermal failures that can take place on this system. Next to that, we got an edge or gateway, an edge layer, which is implemented on the gateway. In this case, the gateway, besides collecting the data and being, the bridge between the physical system and the digital platform, has also some additional features in order to run and to run some models for especially oriented to predictive maintenance. In this case, as I will show later, they are very related to the common mode current sensor, which is used to detect potential degradation in the motor, but also related to a condition monitoring unit, which has different sensors included, which together with some AI models developed during the project is able to detect in advance or somehow to predict potential failures that can take place, again, especially in the motor in that case. Finally, the third layer, it's the complete digital layer. It's a cloud platform which includes different features or subsystems. And in this case, this platform is dealing, besides providing the infrastructure and the high computing architecture needed to run more complex tasks, it's also dealing with long-term failures, meaning that the idea here is to try to monitor some trends or some long-term behavior that after some time may be dangerous or may be the cause for some failures. So in the next slides, I will go more in detail in each of these layers to provide you some an overview of the results that we have been that has been achieved, and especially the technologies that are involved in this digital fault management. So, as I mentioned, the first layer, it's on the local system. All this has been implemented in the local microcontroller that is managing the power converter and driving the motor. As I mentioned, here the idea is to detect or to deal with those critical failures that can potentially damage the motor in very short time, so they require an immediate action. In this case, we are addressing two main components of the integrated motor drive, especially the power converter, in which we are monitoring the temperature on the different semiconductor modules, especially in both silicon carbide and gallium nitride. We also monitor the DC bus voltage and the output voltage of the power converter, and of course the output current that is consumed by the motor. Besides those parameters that are monitored in the power converters, we also have some monitoring systems on the e-motor itself. In this case, what we are looking is especially for electrical and functional faults. From the electrical point of view, of course, besides controlling the temperature, of course, we are also paying some attention to potential sensor faults, because this can be also critical, as, let's say, we'll leave our system completely blind on what is happening in the motor. So checking that their correct operation is also important to ensure the proper operation of the system. And finally, also some functional faults on the motor, which are more related to, again, to the temperature, but also to overspeed and even to the insulation, as I will show later. So in this case, in order to be able to monitor, our power converter includes different sensors that can have been displayed here. They are strategically placed on the key components that we want to monitor, so we are able to collect temperature, voltage, and current data from this place. In relation to the e-motor, the sensors are placed externally in that case, and besides that basic temperature sensor, we also include a common mode current sensor, which is used to detect some potential degradation on the motor insulation, especially on the windings, and also some an accelerometer to conduct some vibration analysis, which together with AI models will be able to provide some estimation of potential or future failures that might happen. Besides these sensors and the direct detection, it's also worth to mention that this on the microcontroller that is in the power converter, fault tolerance operation mode has been implemented in order to ensure the safety and the security of the whole system. So in this case here, you can see a very schematic view of the workflow that this fault tolerant mode is operating on. Basically, the idea is to monitor the different parameters that I've been mentioning, and then based on most of cases at this step is based on thresholds. Okay, one of these thresholds is approaching or overreaching some of the defined values. An error signal is an error flag is raised. In this case, depending on the threshold that has been surpassed, we classify these errors into hard errors or soft errors. In this case, if in the case of hard error, of course, the system requires an immediate shutdown, which is immediately managed by the microcontroller. While in the case of the soft error is detected, which means that it is not that critical but potentially dangerous, a control shutdown is implemented, or on the other side, depending on the situation, a reduced operational mode is applied. In this case, what we do is to limit the maximum voltage and the maximum current that can be applied in order to avoid overheating or overvoltage situations. The idea here is, as I mentioned before, especially to ensure the safety and security of the integrated motor drive, but also to avoid potential dangers, preventing critical damage thanks to this control shutdown, or especially the reduced operational mode. Of course, all this information, as I will show later, is after these potential damages are managed. All this information is shared with through the IoT platform with a decision support system to be used as a log for long-term monitoring, and especially also to register all the issues or incidences that have taken place in order to provide to the user with more information, not just to the user, but also to any operator in charge of maintenance actions or long-term monitoring of the system. Sorry. When it comes to the edge layer, I will try to introduce a little bit the main components that are placed here. So, as I said in the previous slides, we have two specific sensors running on the edge. These are attached to the integrated motor drive externally in order to monitor some specific parameters. The first one is called Condition Monitoring Unit. It's based on a ST microcontroller system, which is called ST-Win. This is basically, as you can see here, a small electronic device which contains quite a lot of sensors, including accelerometers, magnetometers, gyroscopes, and also a MEMS microphone in order that are able to collect data in the range of ultrasound. And all these sensors are linked to an ARM call and AI accelerator. So it means, some processing power enough to run some AI models on the edge. And so we are able, to process on this layer all this data coming, especially from the ultrasound sensor and the vibration, to process them locally and just sending out the outputs or the final results of the analysis. This is quite interesting because, as you know, either the ultrasound data or the vibration data, they require a very high sampling frequency, so meaning that they generate a huge amount of data. Okay, in the case of vibration, we are talking about 10 kilohertz data sampling frequency, which means quite a lot. But in the case of the ultrasound microphone, this sampling frequency increases up to 100 kilohertz. So as you can see, managing all this information or sending to this information, all this data to the cloud in order to be processed later will be costly and won't be efficient simply, okay? It will require a huge bandwidth, it will take a lot of time, a lot of resources. So by doing this local analysis prior to sending the data and just transmitting to the cloud platform the outputs of these AI models is much more efficient and allows for almost near real-time monitoring. Of course, it's not real-time, but quite close. And we avoid, we avoid to over-dimension the whole system just for these two devices. The other sensor that we have included is a current sensor. In this case, it's more similar. It has a Rogowski coil type sensor. And basically, this is to monitor the common mode current in order to identify or to detect potential degradation on the insulation. Both systems are connected to a gateway. In that case, the gateway device we are using is our Raspberry Pi 5, which is complemented with a CAN transceiver, okay, that allows us to communicate with the different systems, as I will show later. And also we included an LTE modem in order to provide some communication on the road. Maybe worth to say that during the project we are mostly using Wi-Fi, but anyway, both types of communication has been tested and there is no issue. It's completely transparent for the user and almost for the system to use either Wi-Fi connection, Ethernet, or the LTE modem. To also on the gateway and again on the edge, As we have just one single device, and as you can see, we need to manage different functionalities, not only with related to data collection and transmission, which is probably the main functionality of the gateway. We also need to deal with those additional sensors. So to do that, we have been implementing a state machine in the gateway, which allows us to parallel run these 5 programs. So basically, as I mentioned, it's the communication with the power controller, with the power converter control unit, and the test bench computer or like any external system that is required. This is done by CAN bus communication, enabling or using maybe the most common communication interface that it's today currently being used in automotive. We also have some additional communication ports. The condition monitoring unit in this case is communicating by USB. Then we have the communication with the cloud, as I mentioned before, either by Wi-Fi or LTE. We got the edge computing capabilities that has been implemented directly on the Raspberry Pi, and finally the communication with the current sensor. Sorry, there's a small mistake here. It's not USB, it's a Bluetooth Low Energy. So at the end, you see, we have been managing and trying to taking profit of all the capabilities of the Raspberry, which is not the most powerful device, but in this case, thanks to the implementation of this state machine, we have been able to implement all these functionalities on this device. Then another critical point, I've been mentioning a lot about the condition monitoring unit and how it helps to detect some potential failures. But of course, this is based on the analysis, especially in this project, we have been focusing on the analysis of the vibration and ultrasound sensors. Of course, probably there are other features that could have been addressed and other parameters that could also be considered for this analysis. But within the project, of course, we have a limited scope and limited time to carry. So we decided to focus on these 2 specific parameters. The analysis, as I mentioned before, is done on the edge layer, basically analyzing all this huge amount of data that is provided by these 2 sensors using some AI algorithms that we have been developing during the project. To do that, of course, we need to do some or to run some experimental tests that allows us to collect the data to train the models. Those tests were carried on a specific test bench using the real motor that has been integrated in the motor drive. This has been done in the facilities of AIT, the Austrian Institute of Technology. And basically what we do is to run the model, to run the motor under different conditions with no load, with a medium load, heavy load, and also some variation of some parameters in order to collect data, to collect as much data as possible to train the model. With this data, we train the model, we run the validation test, also using the same scenario and running the models in order to check if they are able to detect the different conditions. As you can see here, the output was quite accurate. We reached almost a 95% accuracy to predict these 3 classes of values. And what at the end, the information we got from this model, besides these technical parameters of the technical features, are basically 2 things related with the mechanical degradation of the motor. On one side, the vibrations give us information about any potential eccentricity or excessive vibration on the motor, meaning that due to mechanical aging, the axis is gaining some eccentricity, or even if other external components of the motor, are not properly tight, and these are inducing, some movement on the motor. On the other side, talking about the ultrasound parameter, the information or the use of this information that we are doing is to be able to estimate some degradation of bearings. So basically, as the bearings are degrading, the noise is increasing. Of course, when the degradation is high enough, this noise is audible. We can hear that noise, but then probably it's too late. So in this case, the idea was able to be able to detect, in a very early phase, this degradation, so we can actuate and run or to do any operation for maintenance before any critical damage is done. because at this point, maybe, adding some lubricant or quite more simple maintenance activities can solve the problem. Well, if we wait, when we keep this degradation advancing, it will be more difficult, and probably the maintenance will be costly, or perhaps even can have some critical influence or critical damage on the motor. Then moving into the cloud platform, okay, I will, as I've mentioned here, on this digital layer, in this case, we are counting with a whole cloud architecture. So this allows us to provide more complex features. We have more processing power. We have a lot of more capabilities. So we implement different subsystems in this case that all of them cooperate and work together in order to provide a complete solution for the fault management. One of these subsystems, and let's say the core and the common point for all the digital platform is the IoT platform. Okay, this is a complete cloud infrastructure that we have designed and implemented during the project in order to deal with all the data that we are collecting. So this platform is based on the Microsoft Azure services, and also includes some APIs and external interfaces to other technologies. And what this does is basically to provide the infrastructure for data acquisition, okay, also to store and to query the different time series of the data that we are collecting. The idea with all this data is to create a common data lake that, as I will explain later, is that the common database for both the decision support system, the digital twin, and some other features, okay, and the historical data of the whole system. And then also it provides some interfaces with Databricks, which is where some of the AI models are implemented, and also with Neo4j, which is a service that in our case has been used for developing the decision support system. Neo4j, for those of you who are not familiar, it's just a language that allows to create graph databases, okay, that allows to make some relational databases between to manage the different faults and effects that we are dealing with. And finally, we are using React to create the user interface in order to provide the users, either technical or non-technical, with a more friendly interface, and that where they can visualize all the information, but also interact with the system and send the feedback that is required for the system. Another subsystem in this case is the digital twin. The digital twin has been configured as a separate framework, which is interacting with well, initially it was conceived like a separate framework. Then it has been implemented using the Databricks and exchanging information through APIs with our IoT platform. In the digital twin, 3 main models have been included, one for each of the main subsystems of the integrated motor drive, the gearbox, the e-motor, and the power converter. Again, in that case, in order to limit the scope among the whole possibilities and the large amount of possibilities that the digital twin are offering, in this case, we have been focusing on the thermal behavior of the different systems. So the main functionality that we are looking for in this digital twin is to be able to run some simulations on the thermal behavior of each of these components, okay? Of course, this thermal behavior is based on the initial models that we have been that has been developed by the Aarhus University for each of the components using data provided by the component owners. That means that those models provide information about the ideal thermal behavior of those components, or their thermal behavior when they are new. Then what we are doing in order to implement this fault detection, early fault detection or predictive maintenance, is to compare this ideal data with the actual outputs of the gearbox, the e-motor, and the converter. So meaning that for the same operating conditions, we got the ideal behavior, but also the actual behavior. So by comparing them, we can check which deviations have been looking. We can also in the long term to monitor if there's any trend, that it keeps increasing this deviation, which might be an indicator of a potential degradation or potential problems that needs to be addressed. So,
Jose,
yeah.
just a comment, Jose. We are running out of time. Can you speed up the rest of the
For
presentation?
sure. Yeah.
Thank you very much.
Thank you very much, David. Just a few slides remaining. So for the digital twin, as I mentioned, these are the three models. Basically, as I was saying, we can estimate the ideal temperature in one of them based on different input parameters that are listed here. And finally, regarding the decision support system, so what we have do, as I mentioned before, is to create a system that based on the inputs that are provided by the sensors, but also for the other modules, the local processor, the edge processor, and also the digital twin is able to collect and manage all this information in order to relate to a previous database, knowledge database that we have been collecting from the rest of the partners in order to provide information on the potential causes for each fault and of course to recommend actions to be taken. Okay, this is, let's say, the background architecture and the main components of the decision support system. So the starting point are the knowledge fragments, which is the information provided by the different system developers about the potential faults and the behavior of the system. All this information is related into the knowledge graph database, which is also interacting with the different the inference models and the real-time data collected by the system. And then, they are related to the potential faults. And then, of course, we got the user interface with all this information is displayed. Here you can see the user interface for the decision support system. So in number 1, in the square, you can see the log with all the faults or warnings that has been detected. In the number 2 square, you can see this graph database, in this case, very limited. This is just for the fault that is managed at the moment. In the number 3, it's to provide user feedback when either the fault has been addressed or not. And the number 4 is the history of all the operations, and number 5 and 6 are displaying the information about this fault. In number 5, the causes are displayed with the number 6, the recommended actions are provided. Just to finish, I would like to show you some images of the final result of the interface. Here you can see how the IoT platform looks with the different subsystems, the power converter, the electric motors, and the gearbox. This platform has different layers on the user interface. So on the left, you can see the first layer, and then by clicking on each of the subsystems, you can go to a more detailed view, as you can see on the right, with displaying more information about the motor, and then also, as you can see in the right down, some historical data, either on graphs, to see the evolution of the systems. And finally, also a couple of features. Here on the left, you can see the interface for the digital twin. So here we can introduce the different inputs for each model to calculate the output. This can be done manually, either manually in order to get some estimation about the predicted behavior, but also can be filled automatically with the real-time data collected in order to an automatic inference to see this deviation from the ideal conditions that I mentioned before. And just to finish, on the right, you can see an additional feature that we included, which is maybe not the topic of today, but also worth to mention, which is the display of all the environmental and critical circularity information about the system. In this case, of course, the main innovation here is that we are not just displaying static information about the traceability of the different components, the materials that have been used, manufacturing processes, the different certifications and so on, but it's also linked with the decision support system. So we can track also in this part here the different issues that the whole system have been addressing and what if either has been addressed and solved or not. So this help us to provide additional information for reusing or refurbishing and and to improve the circularity of the whole system by considering not just the manufacturing data, but also the history about the operation data from this system. And that's all. Hope it was not too much. Sorry, David, if I exceed the time.
Thank you very much, Jose, for your presentation. We can talk more in detail about the digital twin and so on during the Q&A session. And also, you mentioned about the electronic passport and so on. I think that this will be the topic of the webinar, the last webinar of the next week. So for anyone who is interested, the next week we will talk in more detail about that. So now we have Albert Filba from the IREC talking about the SCAPE project. Hello, Albert.
Hello, can you hear me?
Yes.
Okay, great. Let me share the presentation then. Okay, then you can see the screen, I guess. So welcome everybody. I am Albert Filba. I work as a postdoc or senior researcher now, I think, in IREC, in the Catalonia Institute for Energy Research. And I am also the coordinator of the SCAPE project, which today I will explain you one of the topics that we are developing also in IREC and with other partners from the project, which is the power converter health assessment techniques and digital twin for the electric vehicle. So first of all, let me do a bit of a recap of what has been told in the two past webinars from SCAPE side, of course, to introduce you on the leitmotif of the SCAPE project. So in SCAPE, we are purchasing a method to design the power converters that is based in a basic building block that is what we call the switching cell, which is composed of a power semiconductor, an intelligent electronic fuse, and the ancillary circuit to power these two components and more advanced features, especially for the iFuse. Then from the switching cell, we can build up the converter legs following multi-level neutral point camped topologies. And then with the converter legs, we can then build up the full or the converters, the full converters with any given topology that you can encounter in the literature. Similarly, we have also enclosed the the control into different levels, following also a modular fashion, let's say, where we have the primary control located in the switching cell, which is in charge of driving the main switch and the iFuse and the advanced controls for the iFuse. The secondary control, which is in charge of generating the individual switching cell driving command signals. Okay. And then at the tertiary level, we have the converter control, which is in charge of controlling the converter leg so to deliver the required power to the load, in this case, the motor, since we have an electric vehicle in this example. So with this modular structure, we can easily achieve any given voltage rating and current rating for the converter following the multi-level topologies. Therefore, by increasing the number of levels, we can increase the voltage, and by paralleling the switching cells, we can increase the current rating. Okay, with these properties, then we can really reduce the cost, or we believe that we can reduce the cost of the converters on one side, thanks to the scale economies, since we are using the same switching cell for a wide range of converter families with different voltage and current ratings. And also, since it follows a quite methodic structure, the converters follow a methodic structure, we also believe engineering design effort. And also, last but not least, we are also achieving very high power densities in the converters thanks to the chip embedding technology, where in the right you can see an example of one switching cell board that was one of our first prototypes. Well, it's a second batch of prototypes for switching cells, where here we have embedded inside the PCB the power semiconductor die. So the silicon die inside the PCB. And heat is extracted from the bottom, so this can be directly attached to a cold plate or heatsink. Okay, let's proceed then. Also, and more focused on the presentation from today, in SCAPE we're also developing a health management system for the powertrain. This health management system checks or tries to assess the state of health of the three main elements in the powertrain, which are the battery, the converter, and the motor, using online monitoring systems and digital twins of the three elements. And also, with this information of the state of health, we feed a system, a health management system, which controls the behavior of these three elements with the objective of increasing its lifetime. Since we are focusing on the power converters, we are only seeing this part now. And in SCAPE, we are applying or designing this health management system for the power converters for these two converters that we see on the right of the screen, which are the integrated inverter charger and the battery interfacing converter. These two converters are novel topologies that we have also developed in the framework of SCAPE project. So what is the operating principle of our converters health management system? Well, one of the main elements of the converters are the power semiconductors. And these are prone to degradation, mainly due to thermal and electrical stress. By degradation, I mean that they get old, let's say, and if the degradation keeps going, it may lead to a final failure of the component. And more specifically in SCAPE, the type of power semiconductors that we are using are two. One is the silicon carbide MOSFETs, and the other is the gallium nitride MOSFETs. One for the high voltage switching cell, and the other one for the low voltage switching cell. In both cases, the degradation of these transistors, let's call them MOSFETs as a more general term, leads to an increase of their on-state resistance. Okay. Therefore, this increase on the on-state resistance due to degradation will lead to an increase on their conduction losses, and finally to an increase on their temperature. Their temperature in the semiconductor, but also the temperature on the case or in the printed circuit board, if we consider the case of the chip embedding that I was showing before. So we have designed a state of health assessment system that is based on the online monitoring system, on an online monitoring system that checks the MOSFET temperatures, the case or PCB temperatures, and also on a digital twin of the converters that enclose an electrical, losses, and thermal model. Here on the right, you can see a rough scheme of how this works. We have the converter digital twin, which is fed with the control signals and some ready available measurements from the converter. This digital twin computes the expected temperature of the MOSFETs, and then we have the online monitoring system, which measures the actual value of these temperatures. Then with an algorithm that mainly compares these two values, the computed and measured temperatures, we can determine what is the state of health of the different MOSFETs or switching cells at the end. No? And then this information is fed to the health management action system. The proposed SOH algorithm is quite simple if we consider the conventional two-level converters. especially if there are no parallel semiconductors in the structure. Because then we have a quite linear relationship between the increase on the on-state resistance due to degradation and the increase on the MOSFET's temperature. But in SCAPE, in the multi-level converter structures that we are dealing with or that we have proposed, we have parallel current conduction paths. And this causes at the end a coupling between the switches temperatures, or an electrical coupling which affects their temperatures, let's say. Here you can see an example. For instance, we take these two transistors here, or switching cells that are connected in parallel. You can see that in the no degradation state, where both transistors have the same resistance in on state, then this total current will be shared equally between both. But if one of the switching cells or MOSFETs has an increase on their resistance, for instance, here we can see a double increase of the resistance, we will see that the current sharing is not equal now. But it's modified so that instead of having an increase on the temperature of the degraded switching cell, which is what we expected from the previous slide, we actually see a diminution, a decrease on this temperature, and actually an increase on the other switching cell, which is in good state with health condition. So, yeah, and the coupling effect manifests in the different conduction path, that parallel conduction path that we have in the converter leg. In this case of the inverter. For instance, between these two cells and these two cells that are in parallel, and then also between these four switching cells. I won't go in detail into these numbers now. We can go in the questions if you want. So at the end, to deal with this challenge that comes from this coupling, we have developed a sophisticated state of health algorithm that, well, basically, by comparing the errors between the measured and computed temperatures of the switching cells, not only for each switching cell, but between switching cells, we can determine which is the actual which are the switching cells that are actually degraded. Okay. If you want more details, I have some extra slides to show you on that matter. Then at the end, this algorithm, that is the central piece here, determines what is the scaling factor of the on-state resistances of the switching cells inside the digital twin. These are fed into the electrical model, and then we have the electrical feeding the loss model, the thermal model feeding the loss model, feeding the thermal model, and also going back to the electrical model since everything is coupled, but we manage this easily. And with this, we compute the expected temperature from the measurement that we have in the current sample. Okay. Once all the errors, once the difference between the computed and measured switching cell temperatures are below a certain limit for all the switching cells, we determine that we have reached the correct measure, the correct calculations, the correct assessment of the on-state resistance of the switching cells. And from this, we can compute a simple variable that goes from 0 to 1 to determine what is the state of health of each of one of the individual switching cells. The implementation, the main characteristics of this implementation is that, well, we are relying on economic temperature sensors to measure the switching cell or MOSFET temperatures. Here, for instance, you can see an example where this is a cross-cut of the switching cell, and the die of the MOSFET is here, and here you can see the sensor, which is a very small and cheap sensor, which the communication is also handled in series between the sensors. So it has very low impact in the implementation of the converter at the end. We also rely on readily available measurements, more specifically the output current of the converter leg and the battery voltages. And then the digital twin uses simplified models for the electrical losses and thermal models, so that we can execute it real time in the FPGA that is located in the secondary control level. Here you can see some results of simulations. So far, that's what we have. Here we have a situation where we have an increase of the on-state resistance of these two cells of 50%. And here you can see on the blue traces, the value of the calculated on-state resistance for each one of the switching cells. And you can see that after some transient, the affected switching cells, the computed on resistance for the degraded switching cells matches the degraded one. And here on the right, we have a more complex scenario with degradation of all switching cells at different degrees. And similarly to the left side, you can see that the blue lines get very close to the orange ones, which are the actual value. Then the health actions, also important. What do we do now with the state of health variables values? Well, first of all, with the individual switching cells SOH values, we can obtain SOH value for each one of the converter legs. And then from the converter legs SOH variables, we can obtain an SOH variable for the whole converter. So we have a pretty nice picture of the state of health of the overall power converter. Also, thanks to the switching cell array structures or the multi-level structures of the converters, we have some degrees of freedoms, which, for instance, it allows us to select which switching cell will concentrate the switching losses on each one of the switching transitions. So this way, we can reduce the temperature of the most degraded switching cells and therefore reduce their stress and slow their degradation. We can also deactivate switching cells, for instance, the ones that are more degraded with very low SOH value, and also deactivate the whole converter leg, since, for instance, in the integrated inverter charger, we have 6 converter legs, so we have quite a large degree of fault tolerance in that sense. Also, we can do other actions such as issue predictive maintenance warnings, for instance, to change one switching cell or one converter leg, and also reduce the converter power rating or other variables. In conclusion, in SCAPE, we have devised a simple system to assess the electric vehicle power converter state of health. This is fed. These SOH assessment or variables are fed to the health management system in order to maximize the converter's lifetime and issue predictive maintenance warnings. The SOH system relies on very simple and readily available measurements, so no need for complicated measurements such as the on-state voltage of the MOSFET or the junction temperature. These are very nice, but very hard to implement. And also on a digital twin that uses simplified models so that it can be executed in real time with still good accuracy. And then the degrees of freedom of the switching cell array converter structure allows us to control and reduce the switching cell temperatures and their stress, and also disable close to failure switching cells or converter legs, thanks to the inherent redundancy and fault tolerance of the converter. So that's all from my side. Thank you all for your time.
Thank you very much, Oliver. Thank you for your presentation.
I think I was 5 minutes past the mark, but well, sorry for the next one.
Don't worry. I hope that Konstantinos forgive us all. So, Konstantinos, welcome. Sorry for the delay.
No, it's okay. No worries.
So when you want.
Let me share my screen. Can you see my screen?
Yes.
Okay, perfect. Well, good afternoon, everyone. My name is Konstantinos Kostopoulos, and I'm a PhD candidate at CITHEA UPSE. And over the next 15 minutes, more or less, I will present you the development and the real-time implementation of a digital twin for electric vehicle motors. And this is part of the Maxima project, which focuses on advancing electric motor technologies. And basically, Maxima aims to create a low-cost, modular, permanent magnet axial flux electrical machine with improved performance and with a low environmental impact for automotive market. So, why digital twin matter for electric vehicle motors? The electric vehicle industry faces three critical challenges. The first challenge is the efficiency and the range. Electric vehicles demand higher efficiency and performance. Every fraction of a percentage of efficiency improvement translates directly to more kilometers of driving range. The second challenge is the real-time control. And basically, real-time motor control optimization is critical. We can't just apply generic control strategies because each motor operates in different conditions, different temperatures, different loads, and different driving profiles. So we need an adaptive, intelligent control. And finally, the third challenge is the predictive maintenance. And basically, with the predictive maintenance, we can reduce downtime, and improve reliability. Instead of waiting for a motor to fail, imagine knowing exactly when maintenance is needed, for example. So, what is a digital twin? Well, let me give you a definition of a digital twin. A digital twin is a virtual replica of a physical system, continuously updated with real data. So imagine that the digital twin is a digital copy of the physical system that we have and integrates three critical components. Mathematical models. Here we can find the physical-based equations that describe how the motor behaves under different conditions. And those are not just simulations, they're high-fidelity representations of electromagnetic, thermal, and mechanical phenomena. Then we have the measured data. Here we have real sensor data from the physical motor, like currents, temperature, speeds, rotor positions, and this data flows continuously into the digital twin, keeping it synchronized with the physical system in real time. Then we have the AI algorithms. We can have machine learning models that identify patterns, optimize parameters, and make predictions. And combining these three, let's say, elements, the digital twin enables prediction, optimization, and decision support. And so, imagine this, while the physical motor is running, for example, in your vehicle, the digital twin is running at the same time, performing experiments, testing different control strategies, identify the optimal operation points at the same time. So the best strategies are then applied back to the physical motor. And now let's see where this applies in the real world of electric vehicles. We have three major application areas. The first application is the performance improvement. The digital twin allows us to optimize torque and speed, response in real time, and more importantly, it extends the safe operating area of the motor. With the digital twin monitoring, we can operate closer to the limits while maintaining safety. And this means basically that we can achieve better acceleration, better efficiency, and better overall performance of the system. The second application is the predictive maintenance. And here, the digital twin is able to detect degradation and faults earlier by continuous monitoring critical aspects. And instead of waiting for a catastrophe or a failure of the system, we can identify issues earlier and to avoid a catastrophe, let's say. And the third application is the efficiency enhancement. And so with this application, let's say, the goal is to reduce the energy consumption through the optimal control and load management. And here, let's focus on these specific project objectives. But first, I want to mention that this phase of the project is still under developing. And here we have the key goals of this part of this project. The first goal is to have performance prediction. We want to predict electric machines' performance and especially to predict motor behavior across the entire operating phase, extend the safe operating area using real-time monitoring, and then enable optimal control that adapts to current conditions. The second goal is to have optimal control strategy. We are developing control algorithms that maximize the motor performance within the thermal limits and minimize degradation of critical components such as the magnets, windings, and bearings, and adapt dynamically as the motor conditions change. And the third goal, of course, and our key performance indicator is to reduce the energy consumption. And to achieve this, we are building a multi-physics digital twin platform that considers electromagnetic, thermal, and mechanical phenomena at the same time. Because the reality is that there are not separate problems. A motor that thermally limited can deliver full electromagnetic performance, for example. So our approach respect this interconnection between those three phenomena, and we model the complete system, not just a part of those phenomena. And here we can see the four layers that we have for the digital twin, for the multi-physics digital twin. So the first layer is the physical system, and here we can find this is the foundation, let's say. We have the electric motor with the embedded sensors, and here we can monitoring the AC currents, for example, the motor speed. And then we have the second layer, which is the data acquisition. And all this sensor data from the first layer flows through a canvas and then goes to the third layer in the digital twin models layer, let's say. And this is where the three interconnected phenomena, the electromagnetic model, the thermal model, and the mechanical model are implemented. And then we have the layer number 4, which basically the control output. And here the optimal control commands flow back to the motor controller using the Canvas communication protocol. So we have, let's say, a closed loop system. But in order to do this, we have some real-time implementation challenges to face. And basically, we have 6 major technical challenges. The first one is the computational load, because running electromagnetic, thermal, and mechanical models at the same time can cause bottlenecks. And then we have the execution frequency, because those models, there are different models and they are requiring different update rates. So it's mandatory to synchronize those models in order to exchange data between them. So the one more challenge that we have is the communication latency, because the Canvas may limit the real-time data exchange speed. Then we have the thermal management, and here basically the high processing loads increase the heat in our system, and for this reason we may need a better cooling system, for example. And finally, we have the fault tolerance, and for us it's very critical, this part, because we need to manage error without affecting the overall digital twin operation. This is very critical. So, to address these challenges, we evaluate two fundamental methodologies. The first one is the distributed multi-board integration, and here basically we have some advantages and some challenges or disadvantages to face. And basically, the first advantage is the scalability, because each model will be integrated into a specialized, let's say, board. Then we'll have true parallel execution between those boards. But the challenges here are, first of all, the hardware complexity, because using multiple processors, multiple power supplies, and multiple, for example, cooling systems, the design will be not compact at all, and the synchronization will be a nightmare, because we need to exchange data between those models and, as we can understand, between those boards, and this will be a very challenging part, synchronizing those boards, I mean. Then we have the option number 2, which is the single board integration, and here basically we are using only one board, and we will implement all the 3 models that we have in a single board. The advantages here is, first of all, that we will have one processor, one cooling system, and one power supply, and the design will be more compact. Then the latency will be lower, because all models will share the same memory space, so no network delays between the models. And the maintenance will be more simple, because we will have one device only to manage. But the challenges here, first of all, the processor must do everything, and also the thermal will have some thermal issues, because all computational generates heat in one board, so we may need a better cooling system. So we have selected the solution of a single board integration, because using single board integration, we will have low latency between the models, and also we'll have interboard communication. And a big advantage here is that in the automotive context, you want to minimize the components in order to increase the reliability. So now, from the aspect of the software architecture, I want to tell you some words about the 2 possibilities that we have. First of all, we have the scheduler. A scheduler is basically a simple sequential loop where tasks execute one after another in a specific order, let's say. And the advantages here, as we can understand, is that the code or the whole process is more lightweight, and it's very quick if you want to make some prototypes. But the disadvantages is that we may have task blocking, because if one task runs over time, everything will have to wait. And also, the execution time isn't guaranteed, because sometimes a task will complete in 10 milliseconds, for example, or in 12 milliseconds. And this is very big disadvantage. And Then we have the real-time operating system, like the Zephyr or the FreeRTOS. And what is real-time operating system? Basically, is a real-time kernel with priority-based task scheduling. And the advantages here is that we have predictable timing. Hard real-time guarantees that tasks meet deadlines every time, and this is very important. Also, we have parallel execution using this methodology, and the big disadvantage on this methodology is that the code and this approach is more complex. But we have selected to use a real-time operating system in this project because we want to achieve very actually to meet the deadlines every time. This is the main, the most important part for us. But I want to mention here that of course we are using schedulers in the initial phase in order to validate our algorithms, and then in the final project, let's say, the real-time operating system will be our choice. And in the final slide here, I want to present you the complete control implementation. And here is how the digital twin integrates with the motor control system. On the left side, we have the control board with a field-oriented control system. And on the middle, we have the digital twin with a light purple color. And here we can find the three models, the electromagnetic model, which calculates the torque generation, the back EMF, the loss mechanism. And then we have the thermal model. In the thermal model, we have calculations for the temperature distribution in the stator, in the rotor, and the magnets, and also we have the thermal image. And the third model, as you can see, is the mechanical model. And here we have calculations for the motor and the bearing mechanical dynamics, and also we have estimation for the bearing lifetime. And all these models outputs feed back to modify the control strategy. So we have a feedback loop between the control board, the motor, and the digital twin. And everything communicates using CAN-bus communication protocol. And this is not just a simulation running in parallel. This is a closed-loop control system where physics-based predictions actively optimize the real-time motor operation. And thank you very much for your attention.
Thank you very much, Konstantinos, for your presentation. So let's start the Q&A session. So if someone of our viewers has a question, please type the question into the chat. For now, we have two questions. So let's start. We have a question to Albert from SCAPE. The question is if what are the next actions on your project and the future improvements?
Yeah, next actions regarding the health management system for the board converters is mainly to implement the SOH assessment system in the FPGA that it's in each of the control converter legs, and then do experimental tests, of course, to test the digital twin together with this SOH assessment. And then on a more far future strategy or ambition, I foresee that it would be very interesting to introduce artificial intelligence in the SOH assessment based on the data gathered from the sensors and the data provided by the digital twin. And also use that artificial intelligence to fine-tune the digital twin parameters, which is quite a challenge also. Thanks.
Thank you very much, Albert. We have another question, this time for Jose. The question is the following. How did you manage the interaction between the different subsystems of the digital platform?
Well, that's of course we need to manage in different ways. So on one side we got the communication interfaces, which as I mentioned are different in each level. So in this case we are using serial communication for the first for the local layers to collect data from the sensors. Then we have canvas communication, which is the reference for most of the physical system and allows the exchange of data between the systems in the motor, the power controller, and the gateway. Then all this data is sent to the IoT platform through MQTT. And then more base, once let's say the data is acquired, I would say that the core of data sharing is the data lake, which is included in the IoT platform. In this data lake, all the data coming from the sensors, from any other source, and any relevant parameter that we collect and need to use is integrated into this data lake. Later, the different systems, either the decision support system or the digital twin, are addressing this data lake to collect the data they need to perform the operations. So that would be the core system or the core element for sharing data between the different subsystems.
Thank you very much, Jose. Just to remind, if you have some questions, you have to type the questions on the chat. So we have another question, this time for Konstantinos. The question is this one. What is the main challenge you are currently facing in developing the digital twin?
Well, the main challenge is basically integrating electromagnetic, thermal, and mechanical models that run at very different speeds and different frequencies, basically, while keeping everything real time on embedded hardware. So in order to fix this or to face this challenge, we basically plan to use a heterogeneous CPU board, and in one CPU we will run Linux for low order models, and in the other CPU we will run real-time operating system for deterministic timing, and this will split the work efficiently. And basically, using also this approach, we will have a shared memory between the models, and we will avoid to have delays between exchanging data between the models.
Thank you very much, Konstantinos. So at the moment, we don't have more questions. So if there are no questions, I think that we can close the webinar. So I'm just checking if there are more questions or no, but for the moment, no. So thank you all of you for attending this webinar. Thank you the viewers. Thank you Jose. Thank you Albert. Thank you Konstantinos for explaining your research on this really interesting topic. And see you next week on the final webinars of this series, which will be focused on the circularity and the repairability and the eco design of the system related with the electrical vehicles. So thank you very much for attending.
Yeah. Thank you very much.
Thank
Bye.
you. Thank you very much.
Bye bye.
Bye bye.